Today I'm going to speak about Copulas, and I'm very honored, of course, to be here. This is the first time I'm in this group, and I think it's a friendly group. In hydrology, I always have the problem that there are few people in the room whose paper I did not reject. And here, I think this is not the case. So, what I want to tell you is mainly on spatial dependence and on very special things in spatial dependence. We use variograms, covariance functions, etc. But these are all focusing on linear dependence. And linear dependence is, sometimes we make a log transform or some transforms just to make things look better. And what I'm trying to tell you is that there are alternatives. And not only that there are alternatives, we need them. So, I could say that the world is not non-Gaussian, then you may ask me to give some proof for that. But if I say that the world is not normal, then it's enough to read the newspapers. So I have an outline, and in fact, when I was invited, I put together a presentation which could have exceeded the length of a Wagner opera. So could have filled the whole morning, and then I shortened it down. And since Monday, every day I added 2 or 3 more slides, so it will be relatively long and compact things. So, what I want to speak about is copulas, spatial copulas, and one of the major things is asymmetry. That's something what people don't really look at. So, first I have a few questions to you. Let's start. I will show you some pictures, and you have to find out which is upside down. In this case, it is relatively simple. The next one, this is a digital elevation model. You have on the right and the left-hand side, the two are upside down. And you see the scale is just according to the ranks. So it is not in meters or etc. Now, which is upside down and which is correct? This is somewhere, I think, in Spain. Who is saying that the right? So this one is the correct one. Nobody? Then you are all correct. It's the left one which is the good one. Why? How can we recognize it? Because water flows out. If you would have this one, you would have lakes. Full of lakes, yes? So it is something where upside down can be recognized. The next picture, we went a little bit further, we went to the Mars. You can download the digital elevation of the Mars. Now, which one is the correct one? Red is high, blue is low. So who says that the left one is correct? Yeah, you see, everybody say, or most of you say yes, because these are craters. They are deep and not mountains. So we could recognize that. The next one is coming somewhere from the bottom of the ocean. Do you know which one is correct? I don't think so that's that easy to distinguish, but it's always the left-hand side. And why do I show this? Because they are structurally different. So the structure of the high and the lows is simply different. What does this tell us? So it tells us that upside down can be recognized in many fields. And without even knowing the values, it's only in the ranks. We can also recognize that they are structurally different, even if we do not understand the process behind it. And that means that these structures are all non-symmetrical. So there is a lack of symmetry. And Gauss is symmetrical. Gaussian structures are always fully symmetrical. They don't care whether up is down. So what is up and what is down. And what is interesting, there is no way to make them Gaussian, because any monotonic transformation will keep the order. So this is, for what I said, is the first proof, a non-mathematical or visual proof, that the world is partly non-Gaussian. Yes, and that's the first message. So what do we use for dependence? Not only for spatial dependence, but describing dependence is done by covariances, correlations, rank correlations, Kendall's tau, etc. None of them cares about asymmetry. They are all symmetrical measures. So they will never help us to detect these deficiencies. And that is a big problem. This is coming all from the old linear regression straight line principle, and it seems that the world doesn't know that. It is a serious problem, and we may need some measures which can help us to detect these kind of deficiencies. Now, let's have a short introduction to the Copulas. Look at these four scatter plots. These are four scatter plots which all look very different. And you would have very different conclusions drawn from them. But unfortunately, they all come from the same data. I only changed the scales. Log or exponential or etc. The Pearson correlation changed from 0.4 to 0.8. That's not good. The dependence is not, should not depend on the scale where we measure it. And that is a serious problem. Kendall's tau and the rank correlation are at least invariant in this case. They would not give us different results, but Pearson's correlation does. So the idea is now, let's try to find a method which links the data together without looking at the marginals, so that you can transform the marginals as you wish. It should not change. So we look for an invariant, and that is something what you can do with copulas. So what are copulas? Copulas are multivariate distributions which have a very specific marginals, namely all of the marginals are uniform. Okay, so that's what they are. So it is practically working instead of the data space in the rank space. Yes. So if you look, a scatter plot is made from the data. The empirical copula is made with the help of the marginal distribution functions as a pair. And if you look at this one, this was the empirical copula corresponding to all the four previous scatter plots. So this is the dependence, and not the scatter plots themselves. Okay, so I have here the definition of the copula. It is just a few equations just to impress you that this is a scientific presentation and not just telling you odd stories. The important thing is here. This is Clark's theorem in a short way, which says that every multivariate distribution, a continuous multivariate distribution, can be written as the copula, which relates them, and the marginals here in the arguments. So practically, the marginals are glued together with the help of the copula. That is the basic idea. Okay, so and this copula is unique. So it is every distribution, continuous distribution, has its own copula and nothing else. Okay, so here you see different empirical copulas. This is a nice symmetrical one. This is an asymmetrical one where the small values correspond together and the big are not. So here you always see practically this kind of empirical distribution function value of a pair of the x or of the y of the pair. And you see, dependence can be very, very different, and you have the same rank correlation or the same Kendall's tau, etc. So we need something more. Or at least I feel that I need something more. Now, here you see what we use most of the cases. This is the normal copula. The dependence of the normal distribution here now as a bivariate. This is the distribution function and this is the density. And you see the density is completely symmetrical. It looks like an American football, and it shows no difference in small, big and small. And to my experience, this is the rare case. It's much more often that you have non-symmetrical dependence than you have symmetrical one. And then we should look for that. Now, how can we use copulas to analyze spatial data? We can make the assumptions. We assume that the multivariate copula exists for any number of points, and we do something similar as with the variogram. We say that the bivariate marginals are such that if you translate them, then the copula is the same. It does not matter where we take it. It's like the hypothesis for the variogram. Now, how can we find such kind of spatial copulas? We take our data, we transform them either to the rank space, or if we have a theoretical distribution function, then with that, we collect all these pairs. Yes? On one axis you have the one location, and on the other location, and this we could say as it's a kind of generalization of the experimental variogram, and we can also, if we want to have nice pictures, then we can do some kernel smoothing and draw some nice figures. Like here, for example, you see an empirical copula corresponding to chloride. So we took groundwater measurements, chloride concentrations at different locations, and looked at all pairs which were about 5,000 meters from each apart, and we got this kind of copula showing that high values are very likely to come together. Low values, not that much. If you do a kernel smoothing, then it looks much nicer because then you have lots of colors. But you see, here you have relatively strong dependence, and then it deteriorates for the small values. And that's a clear sign of asymmetry. Yes? So now, how do we define symmetry? If you look at a copula like this one, you can say, okay, is it symmetrical with respect to this axis? This was high values where there's low values, or is it symmetrical in this direction? It is symmetrical in this direction, so with respect to this, because we considered each pair twice, x and y and x. So it's by construction this is symmetrical, and there we can say, okay, symmetrical means that the copula density fulfills this equation for the main axis, and this is for the minor axis. So these are the possibilities to have symmetries and asymmetries. Now, how can we measure this? We can measure this, of course. We can define a measure theoretically. It's a third moment. The third moments are always very nice. They capture, for example, for univariate distributions, they are capturing the skewness. And the asymmetry is something like the skewness in a higher dimension. Yes? So we can define these, we can define this also as an empirical value, so directly from our data, and we can create a function of asymmetry. So asymmetry is changing. We have this AH function. This is our first asymmetry. But life is not that simple. There are even other kind of asymmetries, but for that I decided to take a discharge series. I could have taken some cross sections through topography, but the discharge series is much easier for me to understand. And you see here the discharge series, and here it is flipped back. Yes, it is just I changed the order of time. And what is interesting, you can recognize it. You see, this is a typical river which gets rain, and then it slowly gets rid of the water. Rain slowly gets rid of the water. But it is not like that it slowly accumulates and suddenly empties out. So this is a non-reversible signal. We do not flip it up and down, we flip it left and right. And this, let's look how this works in the copula. What do you see in the copula? You see you have quite a lot of data here, because that is a small value followed by a big one, but none here, because a big one is never followed by a very small one. So this is a different kind of asymmetry, not here to here, but here to here. And this is what we can measure, again, simply with this in the copula. And then we have to be careful, because now the vector is not only length, the vector is a real direction. And we can calculate that for fields, and recognize what really happens in these fields. So are they reversible in a certain sense or not? This is how it is constructed. You take these values are very high, have a very high positive contribution. These have very high negative contribution in the copula. It's a very simple thing here. Now, why do we have these asymmetries? You have seen that we have them. In my opinion, it is always a process which is behind it. Something causes these asymmetries. And for that, I took a simple example, what we often use. It's the advection diffusion equations. Here you have the advection, here you have the diffusion. So if you put a pollutant in water, this is how it will evolve. Okay, and then. Now, first I turn this term off. There is no advection. There is only diffusion. At the beginning, I'm starting with a background thing. There, I calculate the rank correlation and the asymmetries. It's fully symmetrical, no problem. Then I add the pollutant and wait a little bit. If I wait a little bit, what happens? We get an asymmetry, a very clear asymmetry for short distances, because the pollutant pollutes its neighborhood and not the whole thing. And then if you go further in time, then this will evolve, it will stay relatively asymmetrical, and if you would wait infinite time, then it would get symmetrical again. Yeah, because it's fully diluted. And that's one thing. We know that diffusion type processes leave us asymmetries. Okay, so this is not an artifact. And it's also interesting to see that this kind of thing tells you something about the age. Or if you look at geological type of processes where you have something where a certain state is kind of frozen, then it tells you something about when it was frozen in a certain sense. Okay, now let's look at the other asymmetry now. What do you think? Where is the water flowing from left to right or right to left? Who says left to right? I'm always asking these questions to see whether you are already asleep or not. And most of you are still not asleep. So that's good. So you see immediately which way the things go. And this is something what you can show very quickly in the asymmetry function. You look, where is the biggest asymmetry, in which direction? And that's our flow direction. And this works not only on pictures, this works on discrete data. We could find, for example, for precipitation, which direction at that given day the precipitation came from. And it was quite reasonable. Here you see also an asymmetrical thing in a radar image. You see the front of the rainfall is very intense, and you have behind it is kind of losing intensity. Yeah, so those things exist. Now, most of you who had PhD students know that you have to keep them happy. So you have to, so what is the way to keep them happy? To give them strange things to do. So what nobody ever has done. So I asked one of my PhD students whether he could tell me which way the wind is blowing on the Mars, on a given part of the Mars. And what did we do? We looked at a desert. It's a Nili Patera desert. I don't think that anyone has ever been there. And we looked at the digital elevation models, and you could see immediately, after calculating the asymmetries, which is the direction in which this kind of sand desert is structured. And we tested it also on the Sahara to be sure that it is good. And we have now a very useful result. We know which way the wind is blowing there. But he was very proud. Me too. So this is what I told you until now is diagnostic. It is, we can analyze things and we can recognize things. But analyzing and recognizing is only a part of this story. We would also like to have models which can mimic this. Okay, so do we have things which can do that? Why would we need it? We would need it for estimation like interpolation and uncertainty, for simulation. I like simulation much more than interpolation, because simulation shows whether you can capture the uncertainty and the whole process reasonably well. We would like to have things which can be conditioned and which are asymmetrical. Most of the theoretical copulas, if you look up a book, are good in 2 dimensions. And they deteriorate if you go to an infinite dimension, and this is what you need for a field. So we have a problem there, but we have one copula what we can always use. It's the normal copula, because it's nice and easy to handle. We can use a normal score transform, but there is no asymmetry, and you cannot put it in. It's gone. It's lost when you do that. Then you can use chi-square type distribution, which is nothing else but a kind of square of a normal distribution. It's a non-monotonic transformation of a normal distribution. It's very unpleasant due to the non-monotonicity to handle its density. And in general also to handle the whole thing. But you can have another idea. And this another kind of idea which I would like to present in the rest of the time is going back to a paper what we published a long time ago. And I think nobody ever read that. At least the citations are very low. And, this is the typical case which demonstrates for me that there is no correlation between how much I like a paper and how much it is cited. At least it is not negative. And that's already good. It would be bad if there would be a negative correlation between those things. The idea is to look at so-called common random fields. It's common random fields and antithetic random fields. What we did there, which is the thing which is the most similar field which has a different spatial structure. So what do? We take the same random numbers. For example, you take a sequential simulation, or what I like much more is this FFDMA, this fast Fourier transform moving average, because it is fast like hell. And with that, you can generate fields. And now you keep the random numbers fixed. You generate the fields with the same random number, but with different structures. So practically here we generated it with a variogram of the length 20. So this is a Gaussian field with 20, 40, 80, and 160. And you see they are similar because the underlying random numbers are the same. But they are dissimilar because the structure is different. So when we generate, then we always change the random numbers. Here I'm changing the structure. And this idea can be used to generate non-Gaussian fields. How do we do that? We take one random field, random numbers, in this case, for example, for the FFTMA, which are independent. We always start with independent when we generate something. We have F tau R is a random field generator for each tau from 0 to 1. So we take not one normal, but we take an infinite number of normals. Yes? So we have an infinite number of normals, and for each we have a realization there. Okay? Always with the same random numbers. And now out of these infinite number of fields, we select something, but we do not select one specific, but we select depending where our values are. So our random field is defined as the minimum of these x taus, where x tau is phi minus 1 tau, which is now the normal distribution function. What does this mean? It sounds very scientific. It's very simple. If you look here, I have 4 different points. Okay? For example, for the blue points, I generated these things here. This is now not tau, it's phi minus 1 tau. Yes, so it's the inverse of the normal. These are all the values which were generated with the different structures at that given point. Yes? And now I take this one where it crosses the diagonal as a definition for this point. For the other point, I will take this one. For this point, I will take this one, and for this, I will take this one. So I'm not sampling according to one single distribution, but I'm sampling according to the values in this distribution. This is a very unusual little construct, and you can use this even of course, in low dimensions, in 3 dimensions. Here you see, for example, oh, that's strange. The ones are, these are also ones, but they are upside down. Things happen. I have a construct, namely where I start with a correlation matrix which is like this, so there is a perfect correlation between the first and the third, and no correlation between the others. And with changing the tau, I'm always changing the correlation matrix, and end up with this one. How does the distribution look like? For the 2 here, 1 and 2, it is independent. For 2 and 3, it is very strongly dependent for small values. For the third, it is very strongly dependent on the high values. And you can do crazy things here. Crazy type of dependencies, and I think that nature is even crazier than we are, because it produces these kind of things. It produces not necessarily this one, but it produces very unusual asymmetrical dependencies. And here we have a family of dependencies, what we can define, which are very, very asymmetrical and very strange. Now, here you see it for a random field. Here up you see the tau, which is changing. This is always the normal. And here you see what we take from that. Okay, so you see that this field is changing, and this field is also changing, but it's different from the other field. So for the small values, it resembles those which corresponded to small taus. And for the high values, it resembles those which were created with the high values. So and it is per definition very non-Gaussian. And that's nice. That's what we wanted. And if you look here, for example, we created the generator so that we took a variogram with a range, with a small range for tau equals 0, and a variogram with a large range with tau equals 1, and in between we just took it linearly. Yes, so this is easy because you do not need too many parameters, and the generated field looks like that. You see the small values are relatively isolated. You see the small range there, and the high values are clumped together in clusters. What you have here is the variogram, and here you see the asymmetry function. This is the asymmetry function which goes up very much because the big ones are clumped together. Yeah. So we have an asymmetric field, and here you see this is what we would get with a normal. So it would be somewhere here. Here you see the Copulas corresponding to different distances. You see that they are asymmetrical for many distances, and this asymmetry decays with distance. Okay, so that was one example. Another relatively crazy example is here with different anisotropies. So you just kind of turn things around. Small values are very anisotropic in this direction. The big ones are practically isotropic. Yes, and you can generate such a field again with this definition that you have of the angle and this ratio, and then you get a field which is again asymmetrical. It is less as asymmetrical than before, but it's very strangely structured. And that's nice. Here again you see the Copulas, etc. And then I could spend the whole morning and the whole afternoon in showing you crazier and crazier examples. You can even combine, for example, a chi-square type thing with a normal. And you get the strangest structures, and especially you could use not only a linear thing, but you could use very different structures in between. Here we have one more. We started with a Gaussian variogram and ended up with an exponential. And you see the small values are relatively nicely structured, smoothly, and the big ones are much less smooth. And you see, this is an example for a negative asymmetry. Yes. So this is again nice, and we have this kind of process. Okay, so how should we estimate the parameters of these fields? And how can we condition these on observations? Because else this is a problem. The parameter estimation is not that simple, especially because in theory we have an infinite number of parameters, and not even the time of a PhD thesis is enough to estimate an infinite number of parameters. But we can do it with, for example, two parameters, one at the end and one at the other end. So we calculate the observed statistics, we select a model, we select some initial parameters, and we simulate fields, and we calculate from the simulated fields, we always calculate these statistics until we match. So we do via simulation. And simulation is cheap. It's horribly cheap. Of course, you do not do an infinite number of simulations, but I'm doing on my computer something like 1,000 discretization in 1,000 points. That's minutes or partly even seconds. So this is a nice way to estimate the parameters. And now, how do we condition? We condition, here you see a simulated field. On the black crosses, we sampled it, and then we tried to simulate conditionally. How do we condition? We condition first on the 0.5 set. That's a Gaussian. Gaussian conditioning is very simple. We invert that, we get the random numbers, and then we modify those random numbers with a few iterations, and it's really a few iterations, and then you get fields like these. Okay, so it's conditioned. Okay, so it's again a very, very flexible. It is a little bit too flexible. It is frightening. It's relatively parsimonic. Of course, we could say it's a joke to say parsimonic if you have an infinite number of parameters. But we use simple models which have a beginning and an end, for example, and then you have twice as many parameters as a Gaussian. That's not much. That's no pain. Can simulate asymmetrical assumptions, but this cannot simulate advectional type asymmetry. That's bad. Now, can we do that? And here you see this is what we do. We just add here a field to the original x star. So we generate these, and then we add a velocity field to that, and take here according to that the samples. And now, for example, the simplest is when you take a constant velocity everywhere in the whole field, and for example, you put it such that for small values you do not take any advection, and for the big ones it is because it's not the clean water which is polluting the polluted one, but the polluted is polluting the clean one. Now again, a simulation, and you see at the beginning until tau equals 0.5 here. We do the same thing as before. We just sample for each point, and when it reaches the diagonal, then we take it. And then here it will begin to move. Hope it will. Yes, here you see it is moving, and with that you will have the trace of this movement in your picture. Here you see the trace of the movement. Here this is when it is frozen at the end, and you see it is clearly asymmetrical. The big values are here on the front, and the small on the other end, and it is even combined with the first. So you can combine the two things and get that. But you can do very strange things. You can take as velocity field vortices. And then you see it will structure differently. I was afraid that my movies do not work. So yesterday I made a few simulations which were frozen. And here you see some of them which correspond to a vortex. But you can have very complex movements in these fields, and that is quite interesting. So I'm at near the end. I have at least 1 minute more. I go back because we can look at the traces of advection. We can look at nonlinear advections. So we can relate somehow the random fields to at least some processes. And I think that this is a very interesting thing. Can we relate things to processes? We can combine these asymmetries. We can take, which I did not show, linear and nonlinear covariates. It's no problem. because it is the same type of relationship. And the nonlinear covariance means, for example, we can say, okay, we have some kind of geophysical measurement which points out the small values. It's not good for the big ones. And that can be taken into account with these kind of models. We can invert these models. That's again, it's relatively simple because it's the common independent randoms what you need for the inversion. 3D, it's absolutely no problem. Unfortunately, I was not asking that people should wear a 3D type glasses here to see the 3D simulations, but 3D simulations are no problem. They can be conditioned. It is absolutely no problem. So I think if I managed to give you the bad feeling that next time when you use correlations and covariances, that you feel a little bit uneasy, then I reached my goal. So dependence is often non-Gaussian and cannot be transformed to Gaussian. Asymmetries occur through processes. Asymmetries can be measured, and asymmetric fields can be generated. And of course, there is a lot more to be explored. It's fun. It's real fun. I enjoyed it always very much. I have to thank my colleague Sebastian Hörning from UQ Brisbane, who helped me, and we did quite a few things together. And of course, I was looking for good quotes, which would say, okay, if you don't use Copulas, you will never get happy, or things like that. But not even Einstein said something like that. So I had to look for something different, and I found that straight lines leads to the downfall of humanity, was said by Hundertwasser, and that the straight line corresponds to the linear regression corresponds to symmetry. So to some extent, I can derive this, or of the crooked timber of humanity, no straight thing was ever made by Immanuel Kant. So those people support me a little bit. So, and in the unlikely event that you are interested in reading things, there are a few papers here, and I'm ready to take your questions.
Wait a little bit. There. Thank you for this wonderful presentation. My father-in-law tells me that symmetry is the intelligence of the stupid. So I could have quoted him. Yeah, exactly. Questions? Yep.
Thank you for a very nice talk. One thing we are a bit concerned about in random fields is the continuity of the properties. So, have you any proofs or seen any directions that you have continuity, discontinuities, or have you investigated, how the change of the kernel would influence these type of things?
We assumed here, in all these definitions, that this is continuous in tau. Yes, it is needed to have to make sure that you have a solution of this equation, because then you have. Okay, well, if I can go back. Then you can, this is a continuous function, this is another continuous function, and this is above this at minus infinity and below this at plus infinity, so there will be a crossing. So continuity is in this sense necessary. You could do non-continuous simulations also. The only problem is that then you have to change the definition. You have to change the definition to something in between.
Yes, because one of the Gaussian extensions is that you have a random kind of size of the step in the Brownian motion, and that creates non-continuous fields. So I was thinking of this in the convection case that you were having.
Yeah. Yeah, so of course, this is all in the possible program of the future. So this is a kind of what I presented here is either published this year or will be published according to the reviewers.
Yeah, so I like to think that if you have good knowledge of the physics, say the advection diffusion process or something else, then the residual part is more Gaussian. Or if you have a lot of data and try to do some complex regression analysis, the noise is Gaussian. But do you think there's still a leakage to the noise process, or how much data do you need? How much do you need to know about the physics before that leakage stops?
I do not think that the residual will help you that much, and especially if you look at processes which are kind of limited. I work a lot with precipitation data, and in precipitation data, the big problem is zero inflation. If you look at 5-minute precipitation resolution of a radar image, then it can be that 70–80% of the image is zeros. And then there you have the problem that you do not have a unique back transformation, and you cannot, but you can still show that they are traces of an asymmetrical process. That's funny, because even the upper 5% can show you that you are not symmetrical. It does not tell you how you are not symmetrical, but it tells you you cannot be Gaussian.
More questions? Yes?
So you totally convinced me that Gaussian processes do not do reality, but you didn't show me how you use the copula. So what you showed me is that you have a process, you define a process which is non-Gaussian, but you didn't use the copula in any of the steps, except for the showing me that something's wrong here. So I was going in here and trying to figure out how do you do geostatistics with copulas, and what's going on here? How do I use the copula?
I'm doing the asymmetric functions are dependent on the copula, so you cannot create the asymmetry without the copula.
You cannot see the asymmetry without the copula, maybe.
The copula.
But you didn't use the copula.
The asymmetry function is defined on the copula.
But that's only observation.
Yes. Yes. So, for example, here, this is here you see it's always the distribution function values.
Okay.
Okay. So it's a rank statistics. It is corresponding to this kind of copula.
Okay.
Yes?
But that's not used in the geostatistics. It's only showing us that.
No, we are using it. Of course, I must say I'm grateful for this question, because every time I'm preparing a few extra slides for possible questions, and for this I have something.
Perfect.
Like here, this is a real field. These are chloride values in the state of Baden-Württemberg, and on the right-hand side you see when it is interpolated in a Gaussian manner, and it's a mean of 100 simulations out of a non-Gaussian measure, and you can also see in a part that the uncertainty looks totally different. So, and all this is done with the help of the copulas. I did not want to tell the word copula for every slide. But
so how is that simulation done?
This simulation is done by first estimating the parameters of this changing process. Yes. Then we transform the data into normal, but only the marginals, because I want to have the same marginals. And then we look at these simulations like this for every single point, and we take the corresponding thing. So this will define a copula. Okay, this defines like every distribution.
Yeah, but in the whole process, you didn't mention copula once. Just you said in the end that that this defines a copula, which with every distribution. So on the whole way, you didn't use a copula.
Yeah, of course, I used the copula of this very specific distribution. This is a very specific distribution which has a very strange copula. For example, like this. This is the three-dimensional copula here.
So you get only the copula, the high-dimensional copula from the process, and do the rank transfer.
Yes.
Thank you.
Yes, because I cannot define the copula directly, but I can define it with the help of a process.
Interesting talks. I have a lot of questions, but I will limit to few. The first is, in fact, a comment. If I change the axis on a plot, it doesn't change the Pearson correlation. I'm sorry. If I do a transformation, it will change the value of the Pearson correlation. But if I just put it in a log scale, the Pearson value is still the same.
Yes.
That's the first point. And after, do we don't learn more by having all these differences? I mean, why unicity would be better than diversity? First question. And second one, if you use like this more ranking based, you are quite related to the, I would say, probably a uniform distribution of sampling. Like your sample need to follow a given distribution. And if you have a biased sampling, do you don't go back to the original problem? And did we not just change a distance problem versus a sampling problem at the end of the day? I mean, we do hypotheses. It is not just another hypothesis that can be not satisfied again, by another issue. I suppose companies doesn't like to sample in some area, like where nothing is, for example.
Yeah, well, going back to Pearson correlation, if you change non-linearly the scale, then of course the Pearson correlation changes.
If you make a transformation.
Yes. So practically, if you take like pH is a logarithm.
But if I display it in a log scale on the graph, it doesn't change the value of the Pearson value.
But you can change the if you look at the Pearson between the logs, is different than the Pearson of the values. Yes. That's what I was saying.
That's a transformation. It's not changing the
It's a transformation, of course. But why should a transformation change our dependence?
Well, you shouldn't.
Yes, it shouldn't. That's it. Why should it? Because it's the same. It's the same values. It is same values, but still, this is not. This has nothing to do with the asymmetry, which was my main message.
Can we continue that over a coffee, perhaps?
Yes.
Quick question from Michael. Can you continue, please, afterwards, and then, yeah.
Thank you very much for a great presentation. Wondering, can you guarantee that you will reproduce the global distribution while conditioning your data for all the possible vector fields you might be using?
That's a very good question. It depends on what you assume what is all. And it's always a question of what is the good as ensemble. And if you would if you would look that this is the ensemble of the Gaussians, then you would say, okay, I sample that. And what I'm suggesting is something here. And then I can sample that also completely. I have a distribution family behind it. So, but it will not go into here. And if by chance it would have a better place here, then I'm wrong. But there are reasons why I'm not doing that.
Okay. Thank you very much, Professor Bárdossy.